suppose you have two vectors v and x, and u and w are subspaces v, and v plus u is same as x plus w. Prove that u is equal to w. When you try to show that two sets are equal, you have to show both way inclusion both ways, right? So suppose u is in u. Okay. Then since v plus u is in v plus u, right? The v plus u is by definition, it's a collection of all vectors that look like this, right? And that's equal to x plus w, right? We see that v plus u is equal to x plus w for some w in w. Okay. Now, what we need to do is we have to show that since u is equal to x minus v plus w, we have to show that this is in w and that's in w, so that's equal in w. That's what we want to show. Okay. So to show that u is a subset of w, you have to show that this small u is in w, but to show that, you have to show that x minus v is in w. That's because if you have two vectors in w, then the sum is in w because w is a subspace. So how do we show that x minus v is in w? Well, we can see that since v plus 0 is in u, v plus 0 is in v plus u, right? And that's equal to x plus w. That means that v plus 0 is equal to x plus w2 for some w2 in w. Agreed? Yeah, we're just using definitions and nothing else. I'm just saying that v plus u are element, it's a subspace that collects elements that look like v plus another vector that's in u, but I specialize it to 0, but because I can, right? But if I do that, v plus 0 will be v in v plus u, but then since our given thing is that these two are equal as affine sets, so we set them equal to each other, but things in here are x plus w for some w, right? So we just call that vector as w2. I want to say w2 because we already have w for something else, right? But now we are almost done. Now that w2 is v minus x, right? That means x minus v is negative w2, that's in w. Right? Therefore, u equals to x minus v plus w. They're both in w, so it's in w, since w is a subspace. And this shows u is a subset of w. And because the original statement doesn't change if you switch x and v and u and w. The statement doesn't change if you change both letters at the same time, right? Switching this and then just copying all the arguments down will give you the opposite inclusion. So opposite inclusion is obtained if x, v are switched and u, w are switched. Sometimes you can do that if you feel lazy. If the statement is symmetric, doesn't have a preference of u over w and v over x, then you can switch things around and end up with the same. Okay, so let's try this question. Prove that a non-empty subset A of V is an affine subset if and only if lambda V plus 1 minus lambda W is an A for all V, W in A and all lambda in F. This, although this F could be a complex number, and in that case, my analogy breaks down. But if your lambda is something between 1 and 0, the meaning of V and W, if you have lambda V plus 1 minus lambda W, and if you divide it by lambda plus 1 minus lambda, that's like a weighted average between two vectors. Okay, so if you turn on lambda as 1, then this is completely 0 and you just get V. So in that case, it's a weighted average with weight 1 and 0. If you put like 2/3 so that this will be 1/3, then it's like V is doubly weighted than W. So V is pulling it stronger. So any one of these will always be on this straight line passing through V and W, and because V is pulling stronger, the ratio between this to this will be 2 to 1 here. It will be closer to V. If it's 2/3 and 1/3, and so on and so on. So varying these lambda values from between 0 and 1 will, if it's completely 0, you'll be here. And if it's 1, you'll be here. And if it's a value between 0 and 1, it'll be values over here as it moves. And of course, if you go further than 1, then now you go this way. You get a straight line passing through these two vectors. And of course, if you have so if you fix V and W and you do this, then you end up with a one-dimensional line. That's what happens. But of course, you might have a completely different vector somewhere, and then in that case, you'll have a plane and so on and so on. Okay, so that's the intuitive understanding of what's going on here. If this seems very strange to you, the geometric picture kind of explains to you what's happening. But of course, if this lambda is a complex number, then that analogy breaks down and you have something even more strange. Okay, but anyways, this is what we have. Now let's try to prove this. What's the textbook definition of a affine subset? What did we say? What's an affine subset? V plus U, okay, for some V in V and subspace U of V. Okay. So since this is an if and only if statement, we have to show two directions. Let's go this way. So going this way, we assume that A is an affine subset, so we have A as V plus U, where U is a subspace and V is some vector. Okay. And what we need to show is that, because I have V and W here, let's rewrite this as X, okay? So for some X and V. So V and W would be two different vectors that look like this. And then for those two vectors, we have to show that this is still in A. Is that good? All right, so let's try that. So suppose VW is in A. Then V would be X plus U1, and then W would be X plus U2, where U1 and U2 are elements in U. Okay, now let's see what this gives us. Then lambda times V plus 1 minus lambda W. Yeah, so we just plug in what we have. Lambda times X plus U1 plus 1 minus lambda times X plus U2. Now expand so that you have lambda times X plus lambda times U1 plus 1 minus lambda times X plus 1 minus lambda times U2. Now, do you see that these two things simplify? If you expand this, there's negative lambda X and positive lambda X, so they cancel, right? So you just end up with X plus lambda U1 plus 1 minus lambda U2. Okay, and I claim that this is in X plus U. Okay, who can tell me why that's true? First, is lambda U1 in U? Because U is closed under scalar multiplication. Same deal here. 1 minus lambda is some scalar, so you can multiply to U2, and of course that's in U. Right? And because these are individually in U, and U is closed under addition, this plus this is in U. So, because lambda U1 is in U, 1 minus lambda U2 is in U, and lambda U1 plus 1 minus lambda U2 is in U. Okay, so that part is done. Let's prove the opposite direction. So, suppose lambda V plus 1 minus lambda W is in A for all VW in A and lambda in F. Okay. Then or we can just say fix X in A. Fix an X in A. And the picture that we have in mind is something like this. What's an affine set? It's this, and you add an X and you get that, right? And it doesn't matter which representative you choose from A. You can choose anything, and if you just subtract that X, you end up with some subspace. Okay? This will be parallel to that one. Okay, so what we're going to do is define U as it's going to be a collection of y minus x, where y is in A. Okay, so we fix an element in A, but then once you fix it, then U is just going to be taking away the x, and I claim that with this, U is going to be a subspace, right? Okay. Let's show the three parts of being a subspace. What three things that we should prove to show that U is a subspace?
0, complementary addition, and scale multiplication.
Yes. So A, 0 is equal to x minus x, and that's in U, right? Because I can specialize y to be x, right? B, it's closed under addition and closed under scalar multiplication. So let's do this addition first. If y1 minus x and y2 minus x are in U, okay, then y1 minus x plus y2 minus x. See, the thing is, if I can show that this is in A, okay? If I can show that this is in A, then it's in U. We're done, right? So I need to show this, but to show this, we better have this being true. Okay, so if I have lambda as 1/2, then for any two vectors I have 1/2 v plus 1/2 w in A, given that v and w are in A, right? So let's see what that tells us. I know that 1/2 y1 plus 1/2 x is in so okay, good, yeah, is in A, because x and y1 are both in A, right? So in here, I'm assuming that y1 is in A, x is in A, y2 is in A, right? Okay, so by the same way, we can do 1/2 of y2 plus 1/2 of x in A as well. Okay, but look, I need y1 plus y2 minus x, right? So what I can do is I can apply this one again, and I get sum of these two guys. So what do I get if I add these two? I get 1/2 y1 plus 1/2 y2. Sorry. I should be taking half of this plus half of that, right? So I have 1/2 of 1/2 y1 plus 1/2 x plus 1/2 of 1/2 y2 plus 1/2 x in A, right? Which is 1/4 y1 plus 1/4 y2 plus, what is it? 1/4 x plus 1/4 x, so it's 2/4 x. I don't like it. Why? Because I need y1 plus y2 minus x, but this is like, there's a 1/4 and plus 2x. So it seems like a fail, but see, I can choose anything for this one, so why not? See, I know that this is in A and x is also in A, so apply this with lambda being 4. How's that? Yeah. So I guess the moral of this solution is don't give up. Yeah, that's the lesson, okay? It seems like, oh, I can never get this, but just keep trying, it works out. So you take 4 times this, plus 1 minus 4 times x. And this is in A, that's what we know, right? And 4 cancels, so what do you get? y1 plus y2 plus 2x minus 3x is in A. Boom, what do you see? y1 plus y2 minus x is indeed in A, exactly what we wanted to prove, right? Okay? So this is now in A because of all the calculations that we did. And honestly, I don't know if this is the most straightforward proof. I would like to know what the actual proof is. If there's some better proof, please let me know, okay? So that's what we have. Therefore, this is in U, because it's some guy in A minus x, okay? And then C, if y1 minus x is in U and lambda is in F, then lambda times y1 minus x is in U. Well, see, the reason that's true is because since y1 is in A and x is in A, we see that lambda times y1 plus 1 minus lambda x is in A. But what's that? That's like lambda y1 minus x plus x is in A, right? And now you see that because this is true, we see that this was our definition of U, right? We fixed x, so something in A, so this is like y, okay? Minus x is in U, but that means lambda of y1 minus x is in U. Okay, so we, therefore we proved all of these are true, so U is a subspace, and that's because one of the things that you have to know is that when you prove something, you need to know where you're going, and to go somewhere, you have to have some intuition of what to do. How did I come up with this set? Well, because I knew that the geometry says you just take any vector and you subtract it, that's going to be your subspace that this affine space is parallel to, right? So that's how I defined it. And because that intuition tells me that it should be a subspace, I write them down, and it should be true. So even if when I got a little stuck in trying to figure out why this is an A, I have to persist because there should be a way to prove it, okay? So I proved all of them, but because of this, by definition, we see now that A is by definition x plus U, right? Because if you just rewrite down what this means, it's exactly this, right? So, and this means that A is a affine subset, okay? That's the definition of being a affine subset, so we're done.